Hello everybody. So in this video we're going to be reviewing domain and range using set builder notation. So we're going to be building off of the lecture from Monday, and we're going to be seeing kind of the definitions that we reviewed being applied. All right, so reviewing domain and range using set builder notation. So if you could go ahead and take out the lecture notes from Monday, and we'll be building on those definitions, right? So let's go ahead and continue. So we're going to work through a handful of problems in this video, and then you'll have an assignment with some more problems from the same set of problems. So we're going to work through some in the class or in this video, and then you'll have some on your own to do. Right. So let's go ahead and continue. So the first thing we're going to do is we're going to define domain. So we're going to define domain using set builder notation. Informally, we know that domain is all the values of x that are used as an input to our function, right? So we know informally that domain is all values of x that are used as an input to this function. But now we're going to go ahead and define this formally using set builder notation. So the formal definition for domain is as follows. So our definition of domain is as follows. Let x and y be sets. Let f that maps from x to y be a function. Then the domain of f is going to be the set of x and x such that there exists a y and y such that f of x equals y. So x and x means we're looking at the x values that are actually used in the function. Right, so this part means so the x and x part means we're only looking at the x values actually used in the function, and there exists a y and y such that f of x equals y means we're looking at the x values looking at the x values for which the function is defined, right? So if the function isn't defined, then there's not going to be a y in y such that f of x equals y. Right? So only if the function is defined does such a y value exist. Right? So these are the two components, right? So x and x such that there exists a y and y such that f of x equals y. So domain, we're looking at the inputs, right? Typically, we think of x as the input set, y as the output set. So this is why I'm going to use this notation x and y. But the most important thing to know is that it's the inputs, right? So x are the inputs that are actually used in the function for which the function is defined. Next thing we're going to do is we're going to look at the range. So we're going to define range formally here. So similar with domain, we're going to begin with the informal definition, right? So informally, range is all the outputs of a function. We can think of the range of a function as the outputs of a function. All right, so now we're going to apply a little bit more formalism to that definition. So let x and y be sets. Let f that maps from x to y be a function. Then the range of f is going to be y and y such that there exists an x and x such that f of x equals y. And similarly, we're gonna break this into two parts. So the y and y, let's match the colors. Y and y is the y values or outputs So y and y means we're looking at the y values or the outputs defined by the function such that they correspond to x values actually used in the function. Right, so the range of f equals y and y such that there exists an x and x such that f of x equals y. So we're looking at the y values defined by the function that correspond to x values actually used in the function, right? And so this point of actually used in the function is going to be a key role, and we'll see that going forward in some of the sample problems. All right. So now we're going to look at some symbols that we'll see in a graph, and we're going to learn how we use these symbols to define our domains and ranges. All right, so for instance, we might see like a function where we have an endpoint. Right? So if a function isn't defined over all real numbers, right? If a function doesn't take all real numbers as its input, then we're going to see an endpoint somewhere on the graph, right? So if a function does not take all real numbers as its endpoint, we're going as its input, we're going to see an endpoint somewhere on the graph. And so if we see an endpoint like this that's filled in, all right? So if the input is filled in, then we're going to know that that point is included in the graph. All right, so what does this symbol mean on the graph? It's going to mean three things. The first thing is that the point is included So that point is included, right? So if that endpoint is on y equals 2, then we're going to include that y equals 2. The second takeaway from this symbol is that All right, so the interval that goes to this line segment or to this function is going to be a closed interval when we see that the dot is filled in. All right? Now, the third thing that we're going to take away is that the type of symbol when we're using our set builder notation to write down this domain of this range, the symbol that we're going to use to represent this interval is going to be the greater than and equal to, or the greater or the less than and equal to. So so if we see the dot, if we see the endpoint with the filled in dot, then we know that the point is included, the interval is closed, and we will be using the greater than or equal or the less than or equal to symbol. Now, what if that endpoint is open, right? So the fact that it's an endpoint, we know that the domain is not going to be all real numbers, right? But now that we see it's open, what else can we tell? All right, so we can tell one, the point is not included. All right, so essentially what we're going to say is that this function comes really close to that number, but it doesn't actually come to that number. All right, so the second thing regarding the interval is the interval the interval is open. All right, so if the endpoint is not filled in, then it's an open interval. And when we go to write that interval using set builder notation, we're going to use the greater than and the less than symbols. Right, so this is what we know if we have that type of endpoint. All right, so let's look at some other key graphical features that will help us define domains and ranges. So if we see a line with an arrow at the end, just one arrow at the end, what this means is that so if we see an arrow on one end of the line, that tells us that the numbers are going to continue toward infinity in one direction. If we see a line with arrows on two directions, then it just tells us that the numbers are going to extend toward infinity in two directions. Right? So we can say that the numbers will continue toward infinity in two directions. All right, so we've been looking at endpoints, we've been looking at arrows. We're going to start being able to start defining domains and ranges. All right, so going forward, we're gonna define domains and ranges using these graphical clues and using our formal definitions using set builder notation. Make this bigger. All right. So let's identify the domain and identify the range. All right, so we see an input set x and an output set y. And we know that this is a function because values of y are being assigned to values of x, and each x only has one y. All right, so we know that this satisfies the definition of a function. All right, so we know that this is a function. All right, so we say let x and y be sets, let f be a function. We've satisfied those two. Let's go ahead and write out our domains. All right. So we can say the domain of f is equal to x and x, such that there exists a y and a y, such that f of x equals y. All right, so let's look at this last part. So remember we said this part here, there exists a y and y such that f of x equals y is, that refers to the x values for which the function is defined, right? These arrows tell us that is a way of defining that function, right? So when x equals 3, -3, the function is defined, and the output of that function is 9, right? When x equals -2, that function is defined, and the output is -1. Same for 4 and 23, right? So we're going to say, what x's do we have such that the function is defined and equals y, right? And so here we're given 3 such x's, -3, -2, and 4. So this definition becomes a finite answer now that we have a function. We can write domain of f is equal to which of these x's, right? So x's are going to be -3, -2, and 4. So now let's do this. Let's do this for the range. What's our formal definition of range? So the range of f is going to be equal to the y's in y, such that there exists an x in x such that f of x equals y. All right, so now we're looking at the y values that are defined outputs of the given x values, right? So let's look at our domain and see which y values do we get, right? -3 takes us to 9, -2 takes us to -1, and 4 takes us to 23. All right, so those are the y's that have been defined by this function. So that's going to be our range. So we can say range of f is equal to -1, 9, 23. So now we can start to see how we apply this formal definition to get specific answers once we've been given an actual function. All right, so once we're given an actual function, we can start to find the numbers that satisfy the definition. Let's look at this one here. Make that bigger. This data expresses cost as a function of the number of apples. All right, so let's look at this part first. This data expresses cost as a function of the number of apples. So far we've been writing like f is a function that maps from x to y, or from a to b. When we have kind of word problems, we can use those words in our definitions of functions, right? So let's define a function. F is a function, right? So we said f is a function that express cost as a function of the number of apples. So it's a function between apples and cost, right? So we can say f is a function that maps from apples to cost. And we want to know what is the set that represents the range of this function. Right, so we're looking for the range of this function. All right, so let's write down our definition for range. So range of f. It's going to look a little different because we've defined our function using apples and cost, but it'll help things kind of make sense here. So range of f, let's say, is going to be y in cost such that there exists an x in apples such that f of x equals y. All right, so we're looking at these values here in cost that are defined by a specific number of apples. Right? So based on this table, we've only defined this cost function for 1, 2, 3, and 4 apples. All right? So we've only defined this cost function for 1, 2, 3, and 4 apples. All right? So the domain of this function is going to be 1, 2, 3, and 4. Since 1, 2, 3, and 4 are the only number of apples that we've defined this cost function for, our range is not going to be infinite, but just those costs that correspond to the domain. All right, so we have 1 corresponds to 20, 2 to 40, 3 to 60, 4 to 80. So that's going to be our range. Our range is going to be the y in cost for which there exists an x in apples such that f of x equals y. So range f is going to equal 20, 40, 60, and 80. 40, 60, and 80. And there's our answer. So again, we've taken our formal definition of range, looked at a specific function that's been provided to us, and now we have come up with a specific answer for the range of that function. Let's continue. What is the range of f of x equals 3x minus 4 when the domain is 3, 10, and 22? All right, so again, we have to remember that range is the y and y such that there exists an x in it such that f of x equals y. All right, so we're only looking at those y's for which there's an x in the domain that allows the function to be defined. All right, so we look at 3x minus 4. We can evaluate that for any number of x, right? There's nothing preventing us from finding f of 158. But we're restricting that. Our range can't be all numbers because the domain is restricted. Right? In this case, the domain is only 3 numbers, 3, 10, and 22. All right, so we're only looking at those values of y for which there is an x such that the function is defined. All right, there's only 3 such x's such that the function is defined, so our range is going to be limited to those 3 numbers. All right, so there exists an x in x such that f of x equals y. This root corresponds to this, that the domain is the domain is 3, 10, and 22. So that's what that symbol, that notation represents. So to figure out exactly what this range is, then let's evaluate the function for each member of X in the domain. All right, so let's say we got X and y equals f of x. Our domain is 3, 10, and 22. All right, so if we take 3, we take x equals 3, then we have 3 times 3 is 9, minus 4 is equal to 5. We take x as equal to 10, and we have 3 times 10 is 30, minus 4 is 26. We take x equals 22, then we have 3 times 22, which is 66, minus 4 is 62. All right, so now we see all these y's. All right, so now we see the y's such that there exists an x where y equals f of x. All right, so those y's are going to be 5, 26, and 62. So now we can write in our answer. Range of f is equal to the set 5, 26, and 62. All right, so let's keep going. So this is a similar type of problem. The graph represents y equals x when its domain is -2, -1, 0, 1, and 2. So let's write down a definition of range so that we have kind of know where we're going. Range of x is equal to the set y and y such that there exists an x and x such that f of x is equal to y. And so again, we're going to create a table. We have x and y equals f of x. We have -2, -1, 0, 1, and 2. So our function is y equals x. So let's evaluate y equals x for each of our x values. If x equals -2, then y is going to equal -2. If x equals -1, y equals -1. X equals 0, y equals 0. X equals 1, y equals 1. And x is equal to 2, so y equals 2. All right. So now we have our set of y's such that there exists an x such that f of x is equal to y. So if we take this -2 here, let's say that I want to say that -2 is in the range. Is there an x such that f of -2 Is there an x such that f of x is equal to -2? In this case, for this function, there is an x, which is -2, that equals -2, and it's included in the function. So let's go ahead and write our range. And so there's our answer. So we've seen how we can make tables. In these two problems, we can make tables to find the range. Number 8 also uses a table. We can see how we can use these maps between sets to find the range. So we have maps between sets, we have tables. Now we're going to look at, I'm going to skip this problem because it's essentially the same as this one. I'm going to look at these two here. Let's leave it like that. So this is the same function. For number 13, we're identifying the domain. For number 14, we're identifying the range. So let's do these two. Remember earlier we said we needed to look at the arrows, right? So we can look at graphical features to help us define domain and range. So now we're going to see that there's arrows in both sides of this line. All right, so this is a linear function. Looks like the function f of x equals x. So, and since there's arrows on both sides, it extends infinitely in both directions. All right, if it extends infinitely in both directions, then we know that its domain is going to include all numbers. All right, so its domain includes all numbers. Now, the range could still be restricted depending on the type of function it is. For example, a sine function is only going to vary between a specified range, and a quadratic function as well. However, linear functions, they're going to go forever up and forever down. So in this case, our range is also going to be all numbers. All right, so the domain and the range for this function is going to be all numbers. The question is, how do we write that in set builder notation? Right, so we say the domain of f is equal to x and x, such that there exists a y and y, such that f of x equals y. Kind of ran out of space, but and we already said the domain is going to be all real numbers, so we just have to write this in set builder notation. Domain f is going to be all x in the set of real numbers. All right, so this translates to all real numbers. Now we do the same thing for y. We see that along the y-axis, we're going down forever, and we're going up. We're going up forever also, so our range is going to be all real numbers. We define our range. We said that range is going to be equal to all real numbers. So we write that in our set builder notation, and now we have our answer. And so let's look at one more problem. In this case, so there we had kind of unrestricted domains and ranges, right? So if I go back, I can say unrestricted domain and range. All right, so this one has an unrestricted domain in range. If I look at this one, I can see that, let's just look at the graph, and see what we notice. To the left and right, we see arrows, right? We see arrows to the left and right. So we know that horizontally, the function is going to go on forever, right? We go infinitely to the left on the x-axis and infinitely to the right on the x-axis. So we know that our domain is going to be all real numbers, right? So we have an unrestricted domain, right? There's nothing in the domain is being canceled out. All right, so, but if we look at the y's, right? If we look at the y's, or the vertical dimension of the graph, we see that in this graph, it never goes below 0, right? We see kind of a vertex at x equals 0, and on both sides of the y-axis, it's positive. All right, so we have a hyperbola here, and the y's never go below 0. So there's no y less than 0 such that there exists an x and x that f of x equals y. All right, so our range is going to be restricted. All right, so we're going to say our range is going to be all y's greater than or equal to 0. Again, we looked earlier at graphical features. We said if we see a point that's filled in, it means that point's included. If I come over here and I look at this point here at 0, we see that it's filled in. So we know we're going to include that 0. Let's take this kind of informal discussion about the domain and range of this function and write our answer formally. All right, so domain of f, x and x, such that there exists a y and y, such that f of x equals y. We said our domain is going to be unrestricted, so we write that as domain f is going to equal x's in the real numbers. There's our answer for domain. All right, so we have unrestricted domain. All real numbers are going to be in the domain. Let's look at the range now. So our range is going to be the y such that there exists an x such that f of x equals y. We said that there's going to be no y's less than 0 that are defined by the function. So our range is going to be all of those y's greater than or equal to 0. All right, so let's just write that down in set builder notation. So our range of f is going to be the set of y's such that y is greater than or equal to 0. And then there's our answer. Okay, so in this video we reviewed domain and range, writing their definitions formally in set builder notation, how to identify domains and ranges from maps of functions to tables to graphs of functions, and how to write out how to identify those domains and ranges and write them in set builder notation. All right, so please watch this video, reference it with the lecture notes, and I'm going to assign some problems to be done just like these so that we practice, right? So practice is going to be the most important thing. So I mentioned in the instructions for the classwork, the set builder notation classwork, that once you learn this notation, once you learn how to read math in the language of math, everything's going to open up to you, right? And that's a promise that I make, right? Just as music is a whole new world once you understand musical notes, the same thing with math. Once you understand the notation and you're comfortable with reading it and writing it, the whole world of math is going to open up. That was my experience with the subject, and so that's why I believe it to be true. So hopefully this video was helpful, and hopefully the exercises will help you build that experience and confidence with set builder notation. Thank you everybody for watching, and I'll see you guys in class. Have a good day.